Alright, hello friends. Welcome back from exam 1. I hope that the exam went well for you. I saw the averages. It was pretty high, I would say, for exam 1, which is actually quite typical. Exam 1 tends to have the highest average other than exam 4. This is because I think exam 1 tests a lot of material that's kind of intuitive for a lot of people, like general chemistry topics, thermodynamics, basic biology. Unfortunately, I cannot say the same moving forward into exam 2 and exam 3. It's nothing close to intuitive. It's a lot of organic chemistry, it's a lot of regulation, it's pure metabolism. It's the kind of things that you will be learning in medical school. So while I say congratulations, I say don't get too comfortable. Make sure that you keep up those study habits you developed for exam 1 and you refine them further moving forward into exam 2 and exam 3. I know it seems very far away right now, but I promise you it'll come up sooner than you think. Unfortunately, Dr. Purich's last lecture is on Monday. Very sad. But what that means is you're done with nitrogen metabolism after Monday. Unfortunately, he taught it during a week when most of you were not paying attention or going to class because of exam 1. But all that material is still very testable on exam 2. Not only is that material testable, he expects you to understand the nitrogen metabolism that was on exam 1 and be able to use it for exam 2. You will see through the formation of carbonyl phosphate, for example. That was an exam 1 reaction, however, it's going to show up in the urea cycle on exam 2. So it is kind of essential that you go back and review all of nitrogen metabolism for this exam. Even though it's technically not cumulative, I know when I took it, I had to review everything from exam 1 to go into exam 2. Although it's not cumulative, you are expected to retain that knowledge. And I'll kind of explain that as we move forward. So I know you're all exhausted, but we have to keep going. And we have to move on to our first cycle, the urea cycle. We're going to have lots of cycles together. It's going to be so much fun, but this is the first one. This is kind of a baby cycle, I would say, compared to the cycles we are going to get into. But nonetheless, it is a crucial one, and since it's your first one, we're going to go through it together step by step, kind of understand the chemical logic behind it. And once we do that, I think you all should have a pretty solid understanding about how this works, and then a solid understanding about cycles in general. So how I'd recommend you guys do this video is I'd grab 3 sheets of just plain printer paper, 3 or 4, and a bunch of different colors. Split the piece of paper midway through with a big line and label one side, the smaller side, mitochondria, and the other side, the cytoplasm. With metabolism, nitrogen metabolism moving forward, it's essential to understand where reactions are occurring. That's a very common test question. So go ahead and do that. And we're going to be going through this kind of quickly. I'm expecting you guys to have to pause this and draw this out. But luckily, that's a good thing about a video is you can go back and do this as many times as you're going to need to. So we're going to start with our first step. So we have this molecule called ornithine here. And then we have carbamyl phosphate. We're going to get into the creation of carbamyl phosphate a little later in this video. But right now, you should be thinking, oh my gosh, that's like CPS1, right? Yes, it is. So, and you know the purpose of carbamyl phosphate is to donate carbamyl groups to other molecules. That's exactly what it's going to do here. This enzyme, ornithine transcarbamylase, is going to catalyze this reaction. The ornithine, this NH2, is going to nucleophilically attack this carbamyl phosphate's carbonyl group right here. The whole normal deal is going to happen. Kick this up, kick this down, kick this out. It's a tetrahedral intermediate. We're going to kick out the leaving group. And we should know by now that phosphate groups like this ones are fantastic leaving groups. They also release a lot of energy, so this is very favorable. And when we do so, we create this new bond between the ornithine and the carbamyl group. And we create this new molecule called citrulline. Okay, so that's the first step of the urea cycle. All we're doing is a nucleophilic attack and kicking out a phosphate group, something you've seen over and over again at this point in this class. So what happens now is we have this little transporter here, and that citrulline is going to leave the mitochondria and go into the cytoplasm. So the rest of these urea cycle reactions are going to take place in the cytoplasm, unless I specify otherwise, which will happen. So take note of where everything's occurring. The creation of citrulline from ornithine and carbamyl P happens in the mitochondria, but now we're moving out into the cytoplasm. This picture's a little dark, I am so sorry, but we're going to go with it. So we've got citrulline, and this is our friend aspartate. This is one of the amino acids you had to memorize, and here it is back again. So as you can see, when I say the class is cumulative, this is what I mean. You are expected to retain this knowledge and utilize it moving forward. Another thing to take note of in this class is when we hydrolyze ATP, if we're using AMP and pyrophosphate or ADP and phosphate. In this case, we're using AMP and pyrophosphate, and you should know that that's driven by the hydrolysis of pyrophosphate, which releases even more energy. So take note of this. This is a very high energy yielding reaction that we're getting at right here. So the chemical logic behind this is not so obvious, so I'm going to explain it on a separate slide. But essentially, the steps for this one are we have citrulline, we have aspartate, and we have ATP. And they're going to react and form, oh, hello, that's not what I intended. Okay, there we go, arginosuccinate. If you look very closely, you can see that we essentially made a double bond and we stuck aspartate onto the citrulline molecule in place of this carbonyl. A little bit weird, the mechanism's kind of counterintuitive, but essentially all we're doing is just sticking aspartate on top of citrulline to create arginosuccinate. Take note of this argino at the front. It's going to become essential later on. And the enzyme behind this is arginosuccinate synthase, because we're synthesizing arginosuccinate. Now, these enzymes are important for you to remember. You have to know which enzyme goes with which reaction. That could be a test question right there. Which enzyme catalyzes this reaction, and you would have to know. Also, he could easily pull up this reaction and ask you if it's AMP and PPI or ADP and PI, and you would have to know that. These are the little things that actually get you a lot on the exam. So this is this reaction, and just for a little bit of kind of how I do these things, I always put the enzymes in a little green box like this one. So yeah, that's that one. Oh, hello. Sorry, I'm still getting used to this. Alright, so this is the mechanism behind arginosuccinate. So, there we go. So essentially what's going to happen is we're going to have this NH2 donate in. It's going to form a double bond, putting a positive charge on the NH2. It has way too many bonds. And that also gives us too many bonds to carbon. So what is those electrons going to do? They're going to have to go and attack something. When they do this, they're going to go to this adenosine. Oh, that was a beautiful pronunciation there, but whatever. They're going to attack this phosphate right here. So what they're going to do is they're going to put this as an AMP group. They're going to put the AMP group on our citrulline molecule. This is PPI. This is going to get hydrolyzed, releasing a ton of energy. So we have a citrulline AMP intermediate kind of thing going on. You don't need to know the names of the intermediates or anything like that. Just understand that we put AMP on here. At the same time, hydrolyzing pyrophosphate, which is very, very favorable. That's why we have this double bond form right here. Okay, so then this is aspartate. It's going to come and it's going to attack right here. When it attacks this double bond, again, way too many bonds going on, it's going to kick this up, it's going to kick this down, and this is going to leave. And this means we're going to release AMP. As you can see, we released AMP, and we created arginosuccinate. That's the double bond we created, and that is the aspartate we added on. So essentially all aspartate is doing is nucleophilically attacking and releasing AMP once we have it on there. So I would write this down and draw this out so you can see it. Now, disclaimer, my arrows are not 100% correct here. They're just so you can visualize it, not necessarily the complete correct organic chemistry arrows, because that would take me forever to draw, and you don't honestly need to know that for your exam. So yeah, recap. We got our citrulline molecule. This donates in, this attacks, we add on AMP. and we have a citrulline AMP intermediate, while hydrolyzing pyrophosphate releasing a lot of energy. Then we have aspartate attack, kick off the AMP, and we get arginosuccinate, and this is all catalyzed by arginosuccinate synthase. Awesome. All right, so I would have written this on a separate sheet of paper. Cool. So you should have one sheet of paper for your main mechanism, for your main cycle, and a few sheets of paper for the different mechanisms we're going to draw out. Okay. So now moving on a little bit to our next reaction. So we're still kind of at the top part of our paper. So this was our first step, ornithine transcarbamylase. We went from ornithine and carbamyl P to citrulline. We left the mitochondria into the cytoplasm. We had citrulline, aspartate, and ATP. Through arginosuccinate synthase, we went to arginosuccinate. Now we have this enzyme, remember, still in the cytoplasm, called arginosuccinate lyase. And now if you remember, lyases do elimination reactions. So what we're going to end up with is arginine and fumarate. Now, when I said arginosuccinate, that should have tipped you off that arginine was involved in this situation. Again, you need to know what arginine looks like still, and that was from exam 1. And so were lyases. Those were also from exam 1. If you know what a lyase does, it's going to make your life so much easier. Because you're going to have to know what a synthase is, what a transcarbamylase is, and if you know what enzymes tend to do, there's something ahead above me making a lot of noise, so if you hear that, I'm so sorry. It's the Shan's helicopter. But anyway, so arginine, arginosuccinate, and we also have this thing called fumarate. So we're going to go down and we're going to do this mechanism together. So this is an elimination reaction. So we have our arginosuccinate, we're going to have our base attack, grab this hydrogen, kick these electrons here, forming a double bond. At the same time, this is going to go, there's too many bonds right now, grab a hydrogen. This is all happening in an enzyme, so it's super fast, it's immediate. And what this is going to do is force this to be eliminated and keep this NH2 on the molecule. So essentially, what we're doing is we're kicking out this molecule, which is called fumarate, and we're taking this NH2. This NH2 came from our aspartate, and the rest of aspartate is released as fumarate. So we are left with arginine, because we stole that NH2 essentially from aspartate, then immediately kicked it off as fumarate. So yeah, we added aspartate to take its nitrogen, and we eliminate the rest as fumarate. Simply attack, create a bond here. Yeah. So that is arginosuccinate lyase mechanism. You're never going to have to draw this out or anything like that. Just make sure you can kind of see it in your head. It'll help make it a little bit easier how we get from arginosuccinate to arginine and fumarate. As you can see, arginosuccinate, arginine, fumarate. So this guy came from the aspartate. All right, moving on. So now we're starting to get somewhere. So, okay. There we go. So the next enzyme in the urea cycle is arginase. If you remember this from exam 1, arginase is going to hydrolyze. So this H2O is going to do a hydrolysis reaction. It's going to nucleophilically attack right here. And when it does so, we are essentially going to kick this entire thing out as urea. I know you can see it. We've got three NH groups right here. When we attack with that H2O, we basically take its oxygen, and we have our two NH2 groups, and we cut this right here, and we have ornithine once again. So we nucleophilically attacked with water, and it's going to be a whole big mechanism that we don't need to know, but essentially all we need to know is we take its oxygen and we rearrange these bonds a little bit. So we have the double bond here, and we have the two NH2 groups coming out of a carbonyl, and that is urea. That is the entire purpose of this cycle, is the creation of this. So if you think about us just cutting this here and adding a carbonyl, then we have created urea, and we are back to ornithine. Cut this right here, and that is ornithine, my friends. So now, basically what's going to happen is we've regenerated ornithine. We can do this entire cycle again. So we are going to take our ornithine that's in the cytoplasm, and it's going to go through another transporter back into the mitochondria, where it can again react with carbamyl phosphate and make citrulline. So our cycle just regenerated itself. I hope you can see that. If you have any questions about how that worked, how we just regenerated ornithine from our intermediates, it's no worries, just message me and we'll go through it together. But unfortunately, we are nowhere near done with the urea cycle. Those are the main reactions, I would say. However, there's this entire little, on Dr. Purich's slides, he has like 3 different slides showcasing the urea cycle, and if you notice, he added a bunch more reactions into those cycles. You might be wondering why. Well, those are all reactions from exam 1. So, scrolling down a little bit. Those all look familiar, right guys? Yeah, these are all from exam 1. But they're very involved in the urea cycle. They're involved in creating carbamyl phosphate. So, we're going to go through these. Hopefully you still remember what all of these do. I'm going to go through it a little bit fast, but I believe in you guys. So, we have an amino acid. It's floating around in the cytoplasm. We want it in the mitochondria. There's a transporter that's going to take us into the mitochondria. Okay, so now we're in the mitochondria. We have our amino acid, and we've also got this alpha-ketoglutarate lying around. And I know that you guys remember that when we have an amino acid and an alpha-ketoglutarate, we can use our transaminase enzyme to turn our amino acid into its alpha-keto acid form, giving the nitrogen group to alpha-ketoglutarate, forming it into its amino acid form, glutamate. So we have just went from our amino acid, we have donated its NH group to alpha-ketoglutarate through a transamination reaction to make glutamate, while releasing its alpha-keto acid, but we don't really care about that right now. Awesome. So now we're at glutamate. So we've got some NAD plus and glutamate. What is that, guys? It's GDH, glutamate dehydrogenase. And when you have glutamate dehydrogenase, basically what we're going to do is we're going to end up with alpha-ketoglutarate, NADH, and NH3. We oxidatively deaminated it, guys. We created that energy carrier. We went back to our alpha-ketoglutarate that was originally here, making this able to go again. We also released free ammonia. We know that the whole purpose of the urea cycle is to take that free ammonia and to prevent it from harming our bodies, right? So that's the whole point of this reaction. So now that we have NH3, what we can do is we are going to take our NH3, we are going to take bicarbonate, and we are going to take 2 ATPs, and through the enzyme CPS1, we will create carbamyl phosphate, which goes into the urea cycle. Now, it's important to recognize that this is a committed step of the urea cycle. CPS1 is the committed step. And this is because we're directly using 2 ATPs there. That's a lot of energy investment, right? So that is why it's the first committed step of the urea cycle. Remember that it is the committed step. Oh, when he says something is a committed step, you should take that to memory. That is probably going to be a test question. So here is, in case you forgot, the mechanism of how we get from bicarbonate to carbamyl phosphate. Just so you can see, so we've got bicarbonate, we're going to phosphorylate it right here using ATP. We've created a great leaving group. Our NH3, our free NH3 group is going to attack, and we're going to end up with carbamate. When we do so, we can again phosphorylate it right here, creating carbamyl P, so we can add this carbamyl group onto other molecules, like ornithine, because this is such a great leaving group that things are going to be able to attack and kick this off, adding that carbamyl group onto other molecules. So that's just a review. These arrows are not right, sorry about that, of how we get from bicarbonate to carbamyl P. The CPS1 reaction is very important here. So this is our first kind of look at regulation. A few notes about regulation. Most of it is allosteric regulation. If you remember, that means things don't bind to their active site. They bind to other places on the molecule, changing the configuration a bit to allow things to happen or not, basically. When you see this little like circle with like a triangle in it, that is like convention for something that allosterically activates something. If you see the same like circle with an X in it, that means it allosterically deactivates the reaction. So moving forward, that's a little tip. So the most important thing to understand is N-acetyl-glutamate synthase, or NAGS, which I will be calling it for the rest of this video because I cannot say this very well. So this is how we create NAGs. We use glutamate, we use acetyl-CoA. Those are the two reactants to make our product of NAGs and coenzyme. Sorry. So yeah, NAGs allosterically activates our CPS1 reaction, our committed step of our urea cycle. So it's absolutely crucial that we have NAGs around. As you can see right here I wrote the little convention for allosteric activator for N-acetyl-glutamate synthase. So when you're like drawing out mechanisms going forward, you'll be able to see that. Okay, so yeah. So Dr. Purich mentioned that amino acid breakdown leads to more glutamate, and you might be like, that doesn't make any sense. Why would the breakdown of amino acids lead to more of an amino acid? I don't understand. That's okay. So basically, what's going to happen is we're going to break down amino acids. When we do so, we're going to go through a lot of transamination reactions, converting a lot of alpha-ketoglutarate to glutamate. So that's why we have a lot of glutamate when we're going through a lot of catabolism. We're breaking down a lot of amino acids when we're doing things like a high-protein diet, perhaps. But so just so you understand, since glutamate is one of the reactants for the creation of NAGs, with increased glutamate, we have more NAGs. When we have more NAGs, we can allosterically activate CPS1. When we have more CPS1, we have more urea cycle activity because CPS1 is a committed step of the urea cycle. It's also very important to know that arginine will allosterically activate NAGs. And now this is kind of a little bit difficult to think about, but arginine is essential for the urea cycle. So we only really want to go through the urea cycle if we have a lot of arginine around, because we will need to use it in the urea cycle. So just to clarify, NAGs allosterically activates CPS1, but NAGs itself gets allosterically activated by arginine. So arginine and glutamate are both very important in the creation of NAGs. Glutamate because it is one of the reactants, and arginine because it's an allosteric activator. Okay, so a high-protein diet leads to a lot of urea cycle activity. If you think about it like this, the urea cycle, the whole purpose is to get rid of excess ammonia. We don't want a lot of nitrogen floating around in our blood. If we eat a lot of protein, we must break down these amino acids, which means we have a lot of nitrogen to get rid of. So that's why we have to have increased urea cycle activity. All right. So if you've been following along with me, you should get a picture that looks like this. So this is the urea cycle drawn out with everything you need to know. And I'm going to do a little recap of it so we can just kind of go through it one more time together. And also, glucagon, he says in his PowerPoint, is going to allosterically activate all of these enzymes. So make sure you know that glucagon will activate them as well. All right, so we're going to start here. So we have an amino acid. It goes from the cytoplasm into the mitochondria. From there, we go through a transamination reaction with alpha-ketoglutarate, creating glutamate. Once we've gotten glutamate, we can go through GDH to create alpha-ketoglutarate, our energy carrier NADH, and our free ammonia. Our free ammonia will then go through CPS1, and it will react with our bicarbonate and our 2 ATPs to create carbamyl phosphate. That reaction is allosterically activated by NAGs. Once we get to our carbamyl phosphate, our ornithine molecule will nucleophilically attack And our great leaving group here, our phosphate will leave, and we will end up with citrulline catalyzed by ornithine transcarbamylase with our phosphate group leaving. Once we get to citrulline, our citrulline molecule will then leave the mitochondria, going into the cytoplasm. Once we're in the cytoplasm, our citrulline will react with aspartate and ATP, and through arginosuccinate synthase, we will create arginosuccinate, basically just sticking aspartate on top of citrulline. From there, we undergo a lyase reaction. Essentially there, arginosuccinate lyase will give us arginine and fumarate. So essentially, we're cutting it off right here. We're kicking out, I don't know what that was, we're kicking out all of aspartate except for its NH group. We're keeping that moving forward. Then arginase will hydrolyze this bond right here, cleaving it to make ornithine and urea. So our urea is now created, the whole point of the cycle, and we have regenerated our ornithine, which can go back through this transporter, go back into the mitochondria, and start this entire process once again. So yeah, I would make sure you have this down and you understand all of these steps. It is absolutely essential for you to get this moving forward. But if you have followed along with me and created this, you're well ahead, and you are going to really get a head start on your exam 2 studying. So I hope that that was helpful. If not, just message me if you need some clarification or anything like that. You have anything to correct me on, go for that too. Yeah, and I will see you all next week. Have a great weekend, everybody.